Good morning, children. Here we have the next lecture, and as I told you in the last lecture, that this is going to be one of the most important lectures as far as refraction of light is concerned at plane surfaces. Okay, so the heading, as you can see, the main topic or the agenda for the lecture today is the discussion of the critical angle and total internal reflection. Okay, so total internal reflection will come a little later. We will first try to understand what is the meaning of the word critical angle and in what situations does it appear. Okay, so now here there are a few diagrams that I have drawn. These are obviously diagrams in which you can see the ray of light is going to travel from the optically denser medium into the optically rarer medium. Same will be the case throughout. Okay, so I have not written it because of the shortage of space. So we will assume that the rays, all these rays, 4 rays in these separate diagrams, they are moving from an optically denser medium into the optically rarer medium. Okay, so the rule now, by now it should be very clear in your minds that whenever it travels from denser medium to an optically rarer medium, it bends away from the normal. Okay, so if you see in the very first case scenario, this is the ray that is moving and it is falling at an angle of incidence I1, as you can see over here. This is angle of incidence I1, okay, and you can see that this angle of incidence I1 is not very great, is not very big. It's a relatively small value of angle of incidence. So instead of continuously going in that straight direction, in the same direction, the ray has had to bend. You can see this is the normal, so the ray is bending away from the normal because of the denser to rarer rule. Okay, so this angle of incidence I1 is creating an angle of refraction R1 in the rarer medium. Okay, so that's a common process. You know, by now you are very familiar with this process. Now coming to the second case scenario, the mediums are the same. This is the same denser medium, this is the same rarer medium, but the only small difference that you can observe, that you can see if you look at it carefully, is that this angle of incidence of the ray I2, this time it is slightly more than I1. You can see this was I1 and now this is I2. So I have basically increased the angle of incidence. Okay, so again, instead of continuously going straight, the ray has had to bend away from the normal because the same rule applies, denser to rarer, away from the normal. So now you can see that this corresponding angle of refraction, which is R2 in this second diagram, is also coming out to be slightly greater than R1. Okay, why did it happen? Because I increased angle of incidence also, so the corresponding angle of refraction also increased. Okay, so if we keep on doing this with every step, there will be a time, as you can see in the third diagram. Now this is the most important diagram for the understanding of the critical angle. Now in this particular diagram, I increased the angle of incidence even more than I2. Okay, so you can see if you compare number 1, 2 and 3 diagrams, the angle of incidence keeps on increasing. Okay, I1, then it increased to I2, then it has increased to I3. So it was observed that in this particular scenario, what happens is R3 becomes even more, so much more that this R3 actually becomes 90 degree and the refracted ray moves along the surface of separation. As you can see, these are all surfaces of separation. Okay, separating what? Separating the denser medium from the rarer medium. Okay, so there will be a situation, there will be a value of I in the denser medium which will produce a 90 degree angle of refraction in the rarer medium. Now whenever such a thing happens, it is common logic that we will find that the refracted ray is not going to enter into the second medium, but it is just going to glide along the surface of separation. As you can see, this is gliding along the surface of separation. This is that important case of critical angle. So what is the critical angle? This angle of incidence I3 can be called as the critical angle. okay, and it is represented by I with a small c at the bottom, or you can simply write it as capital C, okay. So what we have learned till now is that for all given pairs of media, now you see refractive index word is actually, I have already told you once before, refractive index of any medium cannot be isolated. It is always in comparison to another medium, okay. So there are always two mediums which are being compared. One will be a denser medium, one will be a rarer medium. Similarly over here you see, whatever value of critical angle that we get, this value of critical angle will always be different for different pair of mediums, okay. So let us first understand the definition of critical angle. You see, I have written down the definition, it is there in the book also. Critical angle is that angle of incidence in the denser medium. You see, this is the critical angle, and where is it made? It's made in the denser medium. You see, I have written denser over here. These are all denser mediums. These are all rarer mediums, okay. So critical angle is that angle of incidence which is made in the denser medium, for which or corresponding to which the corresponding angle of refraction in the rarer medium becomes 90. So you can see this is the corresponding angle of refraction in the rarer medium. This is the rarer medium. So I'll write it down once again in case you are getting confused. This is the rarer medium and this is the denser medium, okay. So the corresponding angle of refraction becomes 90 degree in the rarer medium. The moment you see such a case, the corresponding angle I will become your critical angle, okay. So this is the case. Now critical angle obviously can be represented by a capital C or with a small I and C written at the bottom. The critical angle value is different for different pair of media, okay. For example, this denser medium could have been glass, this could have been air. So then in that case, this would have been glass-air pair. Similarly, you can take this denser medium to be water also, this rarer medium to be air. In that case, it will become water-air. Similarly, turpentine, air. So you can keep on changing the denser and the rarer medium. You will keep getting different pairs of mediums, and for all different pairs of mediums, your critical angle will become different. Why will it become different? Because obviously, critical angle is dependent upon the refractive index of the medium, and refractive index of different mediums is different. Okay, so for example, now although you will have a number of pairs of media, you will more or less be dealing with either glass air pair or water air pair. Okay, so the different values are given in the book in the form of a table, but here this is something that you must remember, okay, because every next question is based on glass air pair. So now if somebody asks you what is the critical angle value for glass air pair, you will say that it is 42 degree approximately. Okay, no need to memorize it also, because it will be given in the question whenever you are asked. Okay, but still you will get used to it. Similarly for water air pair, angle of critical angle is 49 degree. So what does this exactly mean? This means that if you have a glass air pair, okay, and you are sending a ray of light from glass into air at an angle of 42 degree, then the angle of refraction that will be made in the air medium will become 90 degree and the ray will glide along the surface. Okay, this is what is the critical angle concept. Okay, now there is always a possibility that you keep on increasing angle I. You see, starting from the first diagram up to the third diagram, we continuously increased angle I, and we reached a situation where the refracted ray glided along the surface of separation. Now what happens if we increase angle I even more? Okay, even more than the critical angle. So let this angle be I4. Okay, let this angle be I4. So this I4 is even more than I3, and I3 was the critical angle. So that means this angle of incidence has become greater than the critical angle now. Okay, this angle of incidence has become greater than the critical angle. So in that case, obviously the ray which was gliding along the surface, now it will have to turn back and come back into the same medium. So this last process is not refraction. In fact, this becomes total internal reflection. So this is a case of total internal reflection. Total internal reflection, I'll explain the word total internal reflection to you. First of all, you must have understood that this is a process of reflection, because the ray is not now going into the second medium, it is coming back. Okay. Now, why total internal reflection? Because in such a case, 100% of the energy that was falling on this surface is being directed back into the same medium. Okay, if you remember, if you take a piece of a mirror, that also produces reflection, but that reflection is not accounting for 100% energy transfer. Here, whatever percentage of energy is falling, that is sent back. So there is a complete reversal, or you can say that 100% of energy that is being falling on the surface, it gets reflected back. Okay, so this fourth case, or the last case, is telling you, is giving you, or is showing you the process of total internal reflection. Okay, now there are a few conditions for total internal reflection. Please understand carefully, have a look at these four diagrams for half a minute, and then I'll give you the conditions for total internal reflection. Okay, so here we are with the conditions of total internal reflection. Now you see, this is the diagram, and I have written case of total internal reflection. This is the denser medium and this is the rarer medium. So the very first condition for total internal reflection to take place is that the ray must be traveling from optically denser medium to an optically rarer medium. If you take it the other way around, the rule that is getting applied will become reverse, or it will change, because you see, whenever a ray of light travels from a rarer to a denser medium, it bends towards the normal. So in that case, it will never come back into the second medium, into the original medium. Okay, so the very first condition, important condition for total internal reflection to take place, is that the ray must always be traveling from a denser medium. So this is the denser medium. Once again, I'll write here, this is the denser medium and this is the rarer medium. Okay, so the ray must always travel from denser medium into rarer medium. Only when it will bend, only then it will bend away from the normal, and slowly, once it keeps getting away from the normal, there will be a time when it will come back into the same medium. Okay, so that's the first condition. And obviously the second condition is that your angle of incidence, these angles at which the original ray is falling, that angle of incidence must be greater than the critical angle. Because you see, in the third case, which was the case of critical angle, till the time angle of incidence is equal to the critical angle, you see, I3 is equal to the critical angle. So this angle of incidence is actually creating the refracted ray to go, it's actually making the refracted ray go along the surface. So it is not coming back, it is going along the surface. Okay, it will only come back if this angle of incidence becomes even more than the critical angle. Okay, so it is this condition that is there, I3 must be greater than IC. Okay, so for this particular rule, you can simply say that angle of incidence must be greater than the critical angle. That's the most important rule that you will have to follow for all necessary diagrams that will come up. Okay, so angle of incidence. So whenever you are given a practical example, you will first of all see whether the ray is going from denser to rarer medium. So if that is okay, the next thing that you will have to check is how much is angle I. Okay, if that angle I is greater than the critical angle, so how will you know the critical angle? The critical angle for a given pair of media will be given. For example, I showed you just now, for glass air pair, you have angle C value as 42 degrees. So you will be given this in the question. Okay, so knowing this particular thing, suppose now somebody gives you this diagram. Okay, now please have a look. Suppose this is glass and this is air. Okay, and this is the scenario, and they are saying that this angle is 45 degree. Okay, you will have to, now this is the question. Supposing that this is the question, you are being asked to complete the ray diagram by showing the refracted ray, if at all there will be a refracted ray. So first thing, is the ray traveling from denser to rarer? Yes, from glass to air. So first condition is true. Now check whether your angle of incidence is greater than the critical angle or not. So you see, your angle of incidence is 45 degree here. Okay, and your critical angle in the question, it is given as 42. So obviously your 45 degree is greater than 42 degree. Therefore the second condition, which is I greater than C, is also correct. So what does that mean? That means total internal reflection will take place. Okay, so the ray will come back into the same medium, and obviously whenever such a thing happens, you have the rule of reflection taking place, law of reflection. Angle I and angle R, they are going to be same. Okay, so this is what is total internal reflection in the practical or the real case scenario. Okay, now had this angle been 42 degree, then what would have happened? Okay, so here is the case that I have drawn, that I was talking about. Now it is the same pair, glass air, so angle C will again remain the same, 42 degrees. Okay, it's fixed for glass air pair. Okay, now your angle of incidence, you can see, is 42 degrees. Okay, so this time your angle I is equal to angle C. You see, C is also 42, I is also 42. Whenever I and C are equal, angle of incidence is equal to critical angle. So in that case, that is the case of the critical angle in which the refracted ray goes along the surface. You see, when the angle of incidence was equal to the critical angle, the refracted ray actually went along the surface, so that your angle of refraction becomes 90 degree. Okay, so that's another case. Now coming to this general diagram that we have, suppose once again we take glass air pair and we are allowing the ray of light to fall at critical angle. Okay, so your angle of incidence is equal to critical angle. So obviously just now we have discussed that the ray will go along the surface, so angle R becomes 90 degree here in this case. So going back to the Snell's law, you see, refractive index of the second medium, which is air here, with respect to the first medium, which is glass here, was given by a formula sin I upon sin R. If you remember, this was the first thing that we had discussed. Refractive index of the second medium with respect to the first medium is equal to sin I upon sin R. So refractive index of air with respect to glass can be written as sine of I. Now this I is nothing but your critical angle here, so you will replace I with C upon sine of R, and R here is 90 degrees. So you have sine of 90 degree, which is 1. So you will simply write sine C upon 1. Okay, so now if you want to change this, you want to write the refractive index of glass with respect to air. Please note, this was refractive index of air with respect to glass, so I have done the reciprocal. So here also it will become reciprocal, so it becomes 1 upon sine C. Please remember this relationship. It is coming from the same Snell's law, but this is the application of Snell's law in a particular case. What is that particular case? That particular case is of the critical angle. Okay, so for critical angle case, you always have I equal to C. For total internal reflection, I becomes greater than C. Okay, so please remember all these things. Now you see, these are a few cases, some questions that can come in your exams. These are in fact the types that come. So we will see over here. First of all, have a look at this particular diagram at the top. This is glass and this is air. Okay, so throughout you will assume that this is glass, and at the top it is air. So there are three rays. I'll label them as A, B and C. There are three rays of light that are trying to enter from glass into air, but all of them are at different angles of incidence. Okay, so your question is to trace the ray of light as and when it moves into the second medium. How does it behave after falling at the surface of separation? So this is the surface of separation. Okay, so these are all different cases that you see. Okay, now let us talk about the first case. Okay, now this is glass air pair, so you will obviously keep in mind that the critical angle value is 42 degrees. Okay, critical angle value is 42 degree. Okay, so immediately you see this diagram over here. The ray C, which is falling, it is falling at an angle of incidence 42 degree, and the critical angle is also 42. So this last case is the case where I and C are equal to each other. So obviously the refracted ray will go along the surface, making an angle of refraction 90 degree. Okay, so this last case is the case of I equal to C, which is the critical angle case. Okay, so critical angle case. Okay, that's one. Now come to the first diagram. This angle of incidence for ray A is 45, whereas angle C, which is critical angle, is only 42. So this means that your angle I is becoming greater than angle C. Okay, angle I is becoming greater. 45 is greater than 42. So this is the condition, if you remember, the second condition for total internal reflection. So here the ray will come back down. Okay, so it will come back into the same medium. Okay, you can use a scale to draw it better. Okay, that's the way it will come back, and obviously this will also become 45 degree. So what is this case? This case is of total internal reflection. Okay, so that's the case of total. So the only case that is left now is the middle one, and you can see here angle of incidence is neither equal to C nor greater than C. It is in fact less than C. So the normal rule applies. What is that normal rule? The light is going from glass into air, so it is going from denser to rarer. It will bend away from the normal. So away from the normal. Okay, so here in this case the actual determination of angle R cannot be done directly by looking at it. You can always apply the Snell's law. Sine of I upon sine of R will be equal to refractive index. Okay, so as far as drawing or completing the diagram was concerned, this is the case. Okay, so please note that these are the type of questions that can be asked. Now coming down to the case of a prism. Okay, now you see, let us first have a look at this prism. This is obviously a 90-45-45 prism. You can also call it as a right angled isosceles prism, because these two angles are 45, so these two sides will also be equal, and this is 90 degree. So right angled isosceles prism, and there is a ray of light that is falling at this particular surface at 90 degree. You can see it is falling right on, straight on, so this is 90 degree. Please remember the rule. Whenever there is an incident ray falling normally to the surface, okay, so this is the surface and it is falling normally at 90 degree, there is going to be no bending. It will continue to go straight. Okay, so it goes on straight. Please remember, I had told you this long back. Okay, so it keeps on moving forward. So that is the first thing that you will draw. You will get 1 mark for it. Okay, now the ray has fallen on the surface of separation again. Now you see, once the ray entered here, this is your glass. Okay, so I can write this is glass and this was air. Okay, similarly this side also you have air. Okay, so now when it falls on this surface, it is trying to enter into air again. Okay, from glass to air, so that is from denser to rarer. Okay, from denser to rarer, so it should bend away from the normal, but not like that. Let us first draw the normal. So the normal at the surface will be drawn like this. Okay. Now, first of all, since we have studied the critical angle concept also and the total internal reflection concept also, this is glass air pair. The ray is trying to go from denser medium into rarer medium. So it is always possible that this could be a case of total internal reflection. So you will have to check. Okay. Please remember, glass air pair, again critical angle is 42. So your C angle is 42. Please remember that. So you will have to find out this angle I first. Okay. If this angle I is 42 degree, then the ray will come out along the surface. If this angle I is greater than 42, then there will be total internal reflection. So how will you find out this angle of incidence? By simple geometry. You see, this is 90, this is 45, so this angle will become 45 degree. Okay, so this becomes 45. The moment this becomes 45, this also becomes 45 because this is the normal. This full angle is 90. Please note, this is the normal. So this full angle is 90 degrees. So 45, 45. Okay, that makes it 90. So your angle I has become 45 degree, whereas your angle C is only 42 degree. That means your angle I is greater than angle C. Whenever you have angle I greater than angle C, total internal reflection takes place. So instead of going into air, the ray will come back. Okay, the ray will come back into the glass medium, which is the same medium. So the moment this total internal reflection happens, your angle R will also become 45 degree. Okay, this is your angle of reflection. So angle of incidence and angle of reflection will both become same. Okay, now when it falls here, again you see, this is glass, this is air. So it is again trying to enter into air. But then since this is 90 degree, how do you know this is 90 degree? Because you see, when this is 45, this will also become 45 because this is normal. This is full. This full angle is 90 degrees. So 45, 45, 45, 45, 90. So the third angle will be 90. So it is falling at normal. So it will continue to move in the same direction. Okay. So there are how many processes are taking place? You see, first is the continuation of that same direction at this surface. Then total internal reflection taking place at this surface, and then obviously again refraction taking place at this surface. Although there is no bending being shown, but then there will be a change in the speed of light. Okay, so if somebody asks you for this question, what is the process or the phenomena that is taking place at this particular hypotenuse side? So at this particular surface, total internal reflection is taking place. Okay, whereas at these two surfaces, refraction is taking place. Okay, so you will have to label all these things, all the arrows, the normal, everything will have to be drawn to get full marks. So if such a question comes, it comes generally for at least 3 marks. Alright, now coming to a similar concept where you are having two rays of light. Okay, you can see that the prism is exactly the same. The only difference between this and this diagram is there are two rays moving. So keeps on going straight. Similarly, this also keeps on going straight. Okay, again you will draw the normal. Again you will draw the normal here also. You can label all the remaining things. The total internal reflection takes it like this outside. Similarly, over here also it takes it outside like this. Okay, so all these angles you will have to label 45, 45, then here 45, 45. Okay, so the reason why I have picked this particular question is, you see, suppose there was an object over here. Okay, suppose there was an object like this. Okay, suppose there was an object here. So through the prism, the ray is going, getting totally internally reflected, and then so you see, this was the arrowhead. Okay, so the image of the arrowhead will be formed here. Okay, similarly, this was the bottom of the arrow, so the bottom of the arrow gets formed here. So you see, what is actually happening is an object which was standing upright like this, after going through total internal reflection through the prism, the image that we are getting, it's actually turned. Okay, it's actually turned. So you see, this was the object. Now it is like, this was the object and it has turned 90 degrees. So you see, this object which was standing straight like this with the arrowhead at the top, it has fallen 90 degrees. So you see, this has actually like a bend of 90 degrees. Okay, so you can say that this is the case of deviation of a ray of light through 90 degree. Okay, so this is the deviation of ray of light through 90 degree. The rays of light were going like this, they actually went down like this. So it's a 90 degree deviation, you can see. Okay, so in the image you can write it as A dash and B dash. So this is deviation of rays by 90 degrees. Okay, that's the case that is taking place here. And please remember that in all such cases we will have 100% energy transfer taking place. Okay, so at this particular surface where total internal reflection is taking place, there will be no loss of energy. As you can imagine in the periscopes also that you discussed, we used to use mirrors. In the 9th standard we had discussed, suppose this was the periscope. Okay, now these were the mirrors that were being used. Okay, so whenever the ray of light actually fell on them, they got reflected like this and then like this. So here the process that was taking place was not total internal reflection, it was simply reflection. So some amount of light was lost in the mirrors, absorbed in the mirrors. So instead of using the mirrors over here, what can you use? You can use the prisms. Okay, so prisms will allow what? The same process, reflection will be there, total internal reflection. The advantage will be the image that we will get will be a very sharp, clear image because there will be no energy loss. Okay, so such cases, such phenomena of total internal reflection can get utilized in saving energy so that we get a better image. So they are used in periscopes, they are used in some kind of binoculars also. Okay. Okay, so here we are with another question on the refraction of light, the total internal reflection. So now on whatever questions you get in the form of such prisms, okay, where a ray of light is entering at a particular angle. Now this angle could be 90, it may not be 90, it could be some other angle. Okay, so the first thing that you will have to keep in mind is that this case could be related with simple refraction also, or it could be related with total internal reflection also. So you will always have to keep in mind the values of angle of incidence and angle of C, which is the critical angle. Okay, so now in this question, let us see, for example, this diagram is given, okay, and you have been told that angle C, which is the critical angle for prism glass, which is this glass, and air interface. Since I told you already that angle C, which is critical angle, will have different values for different pairs of mediums. Okay, so for this particular pair, glass air pair, the critical angle is given as 42 degrees. Okay, now this P is a ray of light which is falling on this particular surface, and as you can see, it is falling normally. We have to trace the path of the ray as it comes out of the prism. Okay, so once it has to enter the prism, and then we'll have to see which side does it come out from. Okay, so the very first thing that you will have to see is that since this ray is falling at 90 degrees, so you can easily use the rule that it will continue to move straight. Okay, since this is a perpendicular incidence, so at this surface there won't be any bending, it will keep on going straight. So you get 1 mark for the correct drawing at this surface. Now the moment it reaches this slant surface, now you see the ray of light is not going to fall at this surface normally, obviously, because this is tilted. Okay, so we will have to first draw the normal at this particular surface. Okay, so You can use the ruler for a better diagram. Okay, supposing this is the normal that I have drawn. So what is my angle of incidence at this surface? Angle of incidence at this surface is this. Now you have to be careful in remembering the basic concepts that angle I and normal, they make the angle of incidence. Okay, so geometrically we have to find out this angle in order to be sure which way the ray will go. Will it come out into the air? Will it go along the surface, or will it come back into the glass according to total internal reflection? Because your C value has been given as 42 degree. So your angle I has to be found out first. That can be found out obviously using simple geometry. As you can see, this triangle over here is a right angled triangle. You can see this angle is 90 degree, okay, and this is 30 degrees. So obviously this angle over here becomes 60 degree. Okay, now once this angle is 60, this was normal. Please note, this was normal. So this full angle, this full entire angle is 90 because of the normal. So if this is 60, this has to be 30 degree. Okay, this angle has to be 30 degree, and this is nothing but your angle of incidence at this surface. Okay, so for checking total internal reflection, the first thing is the ray going from denser to rarer? Remember the two conditions, from denser, which is glass, into rarer, which is air. Okay, so the first condition is true. But is your angle I, which is angle of incidence, greater than angle C? No. Angle I is 30 only and angle C is 42. Okay, for total internal reflection to take place, this angle I should have been greater than 42 degree. Okay, it is not greater than 42 degree. Now check what would have happened if angle I would have been equal to 42. If angle I would have been 42 and angle C also was 42, then the ray would have gone along the surface. But obviously this is neither equal to 42 nor greater than 42. Angle I in fact is less than 42. So that follows the normal procedure of refraction into the second surface. But again with that rule that since it is going from denser medium to rarer medium, it will bend away from the normal. Okay, so your ray of light will go something like this. Okay, so you can draw the refracted ray like this. So since the question had only asked you trace the path of the ray as it comes out, so this is the exact procedure that you will have to do. So one mark over here at this particular surface, one mark for marking of these angles, and obviously one mark for the correct refraction to be shown at this slant surface. Okay, so this is how the final ray P dash, you can call it as P dash, will come out. Okay, if they ask you for this angle of refraction also, this angle R, you can always use the Snell's law at this particular surface. Refractive index of the glass is 3/2, so refractive index is equal to sin I upon sin R. Using that you can easily calculate. Since this question only asked for this, therefore we will end over here. Now we'll have a look at two more examples, then it will be this particular topic will be complete. Okay, so you see here there are two more practical questions that I have taken. The questions that we are dealing with right now are the type of questions that appear in your board exams. Okay, so you please be very attentive while listening to this. Now you see, let us have a look at this particular question. There is a trough of water. I have labeled it over here H2O. So this is a trough of water. This is filled with water, and there is a small pointed object, or a point object you can say. Oh, it can be a coin also, lying over here at the bottom of the container. Okay, and obviously there is air at the top. Okay, what is given? Angle C for water air interface. Now you see these three rays ABC that are emerging out of this object. Okay, they are going to fall at this particular surface of separation and they are going to move into air. So this is denser to rarer. Okay, so this denser medium this time is not glass, it is water. So for water air interface, the value is given in the question as 48 degrees. Okay, so If this is given, they are asking you complete the ray diagrams for A, B and C. All these three rays you have to complete the diagram. How will they come out, or whether they will come out or they will go back into water, and so on and so forth. Okay. So by looking at the three rays, the first thing that you notice is that ray B is falling at an angle of incidence of 48 degree at this surface. You see, this is the normal, okay, for B. So this angle I is 48 degree and your angle C is also 48 degree. So your angle I and angle C, they have matched exactly same. So whenever such a case arises, the ray goes along the surface. So you will simply draw a line on this surface itself, and you can make an arrow like this, and you will write B dash over here. Okay? Why? B dash is indicating that this is the refracted ray for the incident ray B. Okay? So B goes in the direction of B dash. Now, looking at A and C, their angles of incidence are not given in the question. Okay? So how will you determine which way they will go? Okay? So here, even though you have not been given the values, you can always use a little bit of mathematical sense, common sense, or you can say, to determine how much could be the value of this angle. So let's suppose, for example, we take the C ray this time. Okay, this ray C. Okay, have a look at this particular angle. You don't know the exact value of this, but you can easily tell by looking at B that when B was 48, C is much more than that. Okay, you see, the more slant it goes, the more angle I becomes. Okay, so if you keep going away, had you drawn another ray D, the angle of incidence for D would have been even more. Okay, so if this angle of incidence is 48, this angle of incidence is obviously going to be much more than 48. So this angle I is greater than 48 degree. Okay, so it can be 50 degree, it can be 60 degree, it can be 70 degree, doesn't matter, because as long as it is greater than 48 degree, it is always going to be greater than C. Your critical angle is 48. It is set, it is fixed for water-air interface. Okay, so as long as your angle I is greater than 48, what is going to happen? Angle I is greater than angle C case appears. Okay, so for ray C, you can see that angle I is greater than angle C. Okay, so such a case is the condition for total internal reflection. So you can draw a ray which is going to come back into the water, and you can say that this is angle of reflection. So at the ray C is undergoing total internal reflection. Okay, now obviously if you come back to A, you can easily say that this angle of incidence that A is making over here is much smaller than 48. You can see it is visible. This angle I is much less than 48. So this angle I is much less than 48 degree. So in this case, your angle of incidence is less than C. So normal refraction process takes place. Ray will go into air. Now what is the rule to follow? Denser to rarer, so it bends away from the normal. So you can easily draw a ray A dash, which is bending away from the normal. This is the normal. Okay, so these are the three different case scenarios which involve the same pair of medium. Now coming to the last question of this lecture, or of this topic, you can say, this is an equiangular prism that I have taken. Equiangular prism, so that automatically makes all these three internal angles to be 60-60 each. Okay, 60 each. So the other different information given here is angle C is 60. Now although this prism is also going to be made up of glass only, but then this glass must be some different type of a glass, because for this glass air interface your angle C is 60 over here. You must have noticed that for most of the questions involving glass air pair, angle C was taken as 42 degrees. But for this type of glass, we have taken, the question has given us the angle C to be 60 degree. Okay, and this is your incident ray falling. Okay, so as long as it is falling at 90 degree, you can say, you can see over here, you will just produce it forward. Okay, so it keeps on going straight and it falls over here at this slant surface. Now this is denser medium, this is rarer medium, so obviously at this point you will have to first draw the normal and determine the angle I. So I will just try to draw the normal over here. If this is the normal, what is your angle of incidence? This is your angle of incidence. How will you find that out? You will find that out by using geometry, simple geometry. So since this was equiangular prism, all these angles were 60, 60. Okay, right now we will use this triangle over here. Okay, so this is 90, this is 60, so this remaining angle here becomes 30 degree. Okay, now since this is 30, how much will this become? 60. 90 minus 30, because remember this is the normal, so normal always makes 90 degree to the surface. So this full angle was 90, so if this is 30, this will become 60 degrees. This is your angle I. Okay, at this surface, this is your angle I, which is 60 degree. Now you have found out angle I, angle C is already given. Try to check. Is angle I greater than angle C? No, in fact angle I and angle C, they are exactly same. So whenever angle I is equal to angle C, that is a case of critical angle, so the ray will go along the surface. Okay, so this is how you will complete this ray diagram. Okay, so these are the type of questions that will be asked in your exams. There is it is extremely important for you all to practice different kinds of questions. There are many given in the book. We can't take up everything over here, but I'll give you in the assignment that I give you, I'll include some sort of questions that I have not taken. Now those are not different kinds of questions, only separate positioning of the prism. Okay, the concept will be same. So you are only going to attempt those questions once you are thorough with what is critical angle, what are the conditions for total internal reflection to take place, and in what situations all these things happen. Completion of the ray diagrams is extremely important. Now before I close this lecture, it has been quite a big one. You see, I would like to tell you, since these values of critical angle have been given, let's say for glass air pair, the book says angle C is 42, then for water air interface, angle C is, let's say, 48 or 49 degrees. So how are these values coming from? Where? How do you know that the critical angle for glass air is 42, for water air is 49? So you see, we had discussed the refractive index of glass with respect to air just now in the lecture. A few minutes ago we had discussed that this was equal to 1 upon sine C. Okay, now refractive index of glass with respect to air, you obviously know it is, the value is given as 3/2, so this is like 1 upon sine C. So you bring sine C over here, it becomes sine C is equal to 2/3. And in the trigonometric table, you know that when you do 2/3, it comes out to be 0.66, so on. Okay, so the value of the angle for which the sine of that angle is 0.66 is 42. So this is how angle C comes out to be roughly around 42 degrees. Okay, so although this is not to be memorized, or this is not going to be asked, but just a generic piece of information, this one, that how do we come across these values? When the question gives these values, from where is it coming? So it's coming from the same Snell's law that we have applied to the critical angle case. Okay, so this is not that important, but the remaining portions are extremely important.